Hello, my name is Joshua Taylor, and this is my lab report for Lab 1, Constant Velocity. Now, the purpose of this lab is to observe and generate a constant velocity system and then apply Newton's second law to that system. The lab upholds Newton's second law, but fails to produce a system in the real world that experiences a net zero force. The relevant equations that will be used in this experiment are provided here. First and foremost, we have Newton's second law, which is defined as the net force on a system is equal to its change in momentum over change in time.
Rearranging and expanding this definition,
We end up with the velocity update formula, which is the final velocity of a system is equal to its initial velocity plus the net force on the system divided by its mass times the change in time. We'll also be using the position update formula, which is defined as the final position is equal to the initial position plus the average velocity of the system times the change in time. The average velocity is defined as the change in position over change in time. And to find this for our system, we're going to take two very early positions at two very early times, plug them into the formula, and get a velocity that should remain the same throughout the entire experiment as the net force on the system is equal to 0, and we see constant velocity. Now we're going to dive into the physical model and the computational model that was used for this experiment. The physical model is a rolled soccer ball, and we analyzed its motion using Tracker, and the computational model was produced using ClosScript. So for the physical model, we're going to go over to Tracker. And here we can see the system is a blue soccer ball rolling across a table.
anything that is not the soccer ball can be considered the ball's surroundings.
What you cannot see before this first frame is my hand accelerating the ball to its initial velocity, and we're going to end the clip as the ball rolls out of the frame. When playing it, you see the ball's center of mass with red diamonds as it rolls across the screen, and this produces a chart where we have the time of each position of the soccer ball as it rolls across the screen. It's important to note that the length scale for this video was calibrated by using the length of the soccer ball, which is 22 centimeters, and we define the positive x-axis as pointing to the right and the positive y-axis as pointing up. The data produced by Tracker was taken and input into a spreadsheet, and here you can see that data. So next, we're going to generate a computational model, and that was done using ClosScript. I took the Lab 1 starter code and put it in, adjusting the necessary components, such as the ball's mass, its initial position, and initial velocity. That initial velocity was calculated using the initial time and position changes of the ball. The final timestamp of the ball's motion is 1.102 seconds. So in that time span, we're going to apply the velocity update formula as well as the position update formula to generate an illustration of the ball's motion. And when this program is run, it mirrors the motion that we saw in the real-life video. It's important to note that this code sets the net force equal to the ball equal to 0, as seen here, Fnet equals 0, while in real life, there are other forces acting on the ball that will change its motion that will not be projected by this program. Running this code generates timestamps and positions of the ball as it moves through each loop of the while loop. And I took this data and put it in my spreadsheet with the other data from Tracker. The data from the spreadsheet was used to generate this graph, which models the position of the ball in real life from the experiment, as well as the position of the ball from the computationally generated model. You can see that the position in the computationally generated model exceeds the position of the experimental model as time progresses. And that is because the computational model neglects air resistance or drag forces that the physical model experiences and is impacted by. Those forces contribute to a non-constant velocity system, and we see that velocity decrease, which is reflected by a position that does not increase as fast as the computationally modeled position. If I had assigned the positive x direction to be going left, then the balls would be moving in a negative x direction, which would be reflected by a negative slope in the position graph. However, the magnitude of these positions would remain the same. It would just be that direction and slope that changes. Now, what does all of this mean? In the computational model, the net force is equal to 0, which allows our system to experience constant velocity and can be observed from the graphs previously displayed. However, in real life, there are two relevant forces that greatly change the motion of the soccer ball, and an infinitely large number of negligible forces that can generally be ignored, but they still do alter the motion of the system. The two relevant forces are friction and air resistance, and these slow down the soccer ball's velocity and contribute to a position that does not match the computer-generated position graph. At the same time, every object in the universe is exerting a gravitational force on the soccer ball as it moves. And this force is very, very small and is negligible, but it is something to consider when you're thinking about a system that has the net force equal to 0 with constant velocity. In conclusion, this experiment upholds Newton's second law. If there is a net force acting on a system, the system will experience a change in velocity. But if there is no net force, the system will undergo constant velocity. Our model that illustrated a net force of 0 was computational, and it generated a position versus time graph that exceeded the observed position versus time of the real-life physical soccer ball that did not experience net force equal to 0. The real soccer ball had drag forces and air resistance that slowed it down and made it underperform in the position category. However, Newton's second law was certainly demonstrated when you take into account all of these outside forces in the real world. Thanks for watching.